Next question, find the integer n for which limit extending to 0 cos x minus 1 into cos x minus e power x divided by x power n is a finite non-zero number. We have to find the integer n for which limit extending to 0 cos x minus 1 into cos x minus e power x divided by x power n is a finite non-zero number. This answer needs to be finite and it also needs to be non-zero number. So let us see, 1 minus cos x by x square is a standard limit and we can see cos x minus 1 here. So 1 minus cos x by x square is half cos x minus 1. I will borrow x square from this x power n, this limit, it is going to be minus half. So let me replace this limit by minus half, and because minus half is a non-zero finite number, we can write it outside the limit. Now we have to see that as x tends to 0, cos x minus e power x by x power n minus 2 needs to be a finite non-zero number. As x tends to 0, numerator is tending to 0. Cos x is 1, e power x is also 1. So 1 minus 1, it is 0. Numerator is tending to 0. So denominator should also tend to 0 for this ratio to be finite. N has to be greater than 2. So let us assume that n is greater than 2 and proceed further. This is a 0 by 0 form. We can apply L'Hospital rule. Minus half, limit extending to 0. Derivative of numerator, derivative of cos x is sin x, minus derivative of e power x is e power x, divided by derivative of x power n minus 2 is n minus 2 into x power n minus 3. Now this limit needs to be non-zero finite number. This limit needs to be non-zero finite number. Observe, as x tends to 0, sin x tends to 0, e power x tends to 1. So numerator tends to minus 1. Numerator tends to minus 1. As numerator is finite and non-zero, denominator should also be non-zero. As numerator is finite and non-zero, for the limit to exist and to be finite, denominator should also be non-zero. But we can see x power n minus 3 here. So for this to be non-zero, unless power of x is 0, this is going to tend to 0. So n has to be 3. The power of x has to become 0 or n has to be 3. So for the limit to be non-zero finite limit, our value of n, it should be 3. So answer is B. Next question, evaluate limit n tending to infinity log of n to the base n minus 1 into log of n plus 1 to the base n into so on up to log of n power k to the base n power k minus 1. We have to evaluate limit n tending to infinity log of n to the base n minus 1 into log of n plus 1 to the base n into log of n plus 2 to the base n plus 1 so on up to log of n power k to the base n power k minus 1. We have to evaluate limit n tending to infinity log of n to the base n minus 1 into log of n plus 1 to the base n so on up to log of n power k to the base n power k minus 1. Now we know log a to the base b is log a by log b. This question is based on simple property of logarithms, which says log a to the base b is equal to log a by log b. So this limit can now be written as limit n tending to infinity log n divided by log n minus 1 into log n plus 1 divided by log n. We can see log n and log n gets cancelled. Log n plus 2 divided by log n plus 1. We can see log n plus 1 and log n plus 1 gets cancelled. So on up to log n power k divided by log n power k minus 1. Log n power k minus 1, log n plus 2, everything gets cancelled, and we are left with log n power k divided by log n minus 1. So this limit is limit n tending to infinity log of n power k divided by log of n minus 1. Now again we will use a small property of logarithms. Log n power k, we can write it as k log n, and k can be written outside the limit. Log of n power k, it is k into log n. And as n tends to infinity, n is an infinitely large number, and when n is an infinitely large number, n is almost the same as n minus 1. To an infinitely large number, we add or subtract 1, doesn't make much difference in the ratio. So we can write this as log n by log n, and this ratio will be 1, or our answer will be k. So answer is k, which is option C. Let f of x is equal to integral minus 1 to x mod t dt when x is greater than or equal to minus 1. Then we have to see whether option A, f and f dash are continuous for x plus 1 greater than 0. Option B, f is continuous but f dash is not continuous for x plus 1 greater than 0. Or option C, f and f dash are derivable at x equal to 0. Option D, f is continuous at x equal to 0 but f dash is not. So we have to check for continuity and differentiability of the function. F of x is given to be integral minus 1 to x mod t dt whenever x is greater than minus 1. Whenever x is greater than or equal to minus 1, f of x is given to be integral minus 1 to x mod t dt. Now we have to talk about continuity of f and f dash. F of x is obtained by integrating a continuous function. F of x is obtained by integrating a continuous function. So obviously f of x is going to be continuous. F of x is going to be continuous. And even derivative of f of x, f dash of x, by Newton-Leibniz rule, it is given by derivative of the upper limit 1 into substitute x in place of t mod x minus derivative of lower limit is 0. So f dash x is mod x, and mod x we know it is a continuous function. So f of x and f dash x are both continuous, and it is option A. Answer is option A. Next question. If f of x is equal to x minus x naught into phi of x, and phi of x is continuous at x equal to x naught, then we have to find the value of f dash of x naught. Given f of x is equal to x minus x naught into phi of x, and it is also given that phi of x is continuous at x equal to 0. Phi of x is continuous at x equal to x naught. Then we need to find the value of f dash of x naught. Now many students tend to differentiate this equation directly, but nothing is mentioned about differentiability of phi of x. Nothing is mentioned about differentiability of phi of x at x equal to x naught. So we have to start from the basic that f dash x is equal to limit x tending to, we need to find derivative at x naught. So f dash of x naught is equal to limit extending to x naught f of x minus f of x naught divided by x minus x naught. Derivative at x naught for the function f is equal to limit extending to x naught f of x minus f of x naught divided by x minus x naught. Now, f of x naught is 0. X naught minus x naught becomes 0. So, this limit can be written as limit extending to x naught. F of x is how much? X minus x naught into phi of x divided by x minus x naught. Now, x minus x naught and x minus x naught get cancelled. We have limit extending to x naught phi of x. In the question, it is given that phi of x is continuous at x naught. Phi of x is given to be continuous at x naught. So, limit extending to x naught phi of x will be equal to phi of x naught. So, f dash of x naught will be equal to phi of x naught, which is option B. So, answer is option B. Next question, let f of x is equal to x power n sin 1 by x if x is not equal to 0 and 0 when x is equal to 0. Then f of x is continuous but not differentiable at x equal to 0 if option A, n belongs to open 0 to 1, option B, n belongs to closed 1 to infinity, option C, n belongs to minus infinity to 0, and option D, n equal to 0. The question says the function f of x is equal to x power n sin 1 by x when x is not equal to 0 and 0 when x is equal to 0 is continuous but not differentiable. Is continuous but not differentiable. So, we have to find for what values of n this function is continuous but not differentiable. Now, for the function to be continuous, f of 0 minus and f of 0 plus should be equal to f of 0, which is 0. Functional value at 0 is given to be 0 and f of 0 minus and f of 0 plus should both be equal to 0. So, let us evaluate limit extending to 0 f of x. As x tends to 0, because f of x is not equal to 0, f of x will be x power n sin 1 by x. As x tends to 0, x is not equal to 0, so f of x is x power n sin 1 by x. Now, this limit, it has to be equal to 0 because it is given that the function is continuous. This limit has to be 0. As x tends to 0, 1 by x tends to infinity, and sign of a number tending to infinity is ambiguous. It fluctuates between minus 1 and 1. We are not certain what it is going to be, but we are sure that it lies between minus 1 and 1. So, for this product to be 0, it is compulsory that x power n has to tend to 0. As x tends to 0, x power n should also tend to 0, and this is possible only when n is any positive number. If n is 0, x power n is going to be 1. If n is negative, x power n would be plus infinity or minus infinity depending on x is tending to which side of 0, and this will be 0 only when n is positive, and this should compulsorily be 0 because the function is given to be continuous. So, n has to be positive. N should be greater than 0, and the function is also non-differentiable at 0. The function is also non-differentiable at 0. For that, limit x tending to 0 f of x minus f of 0, which is 0, divided by x minus 0. limit extending to a, f of x minus f of a divided by x minus a, that is derivative. This limit should not exist. If it exists and is finite, then the function will be differentiable, but it is given that the function is non-differentiable. So, limit extending to 0, x power n sin 1 by x divided by x, this limit should not exist. Or the limit extending to 0, x power n minus 1 sin 1 by x should not exist. This limit should not exist. Now, sin 1 by x as x tends to 0, we know lies between minus 1 to 1, but we are not sure what it is going to be. So, for this limit not to exist, either this has to be 1 or this has to be infinitely large, but this can't be 0. This can't be 0. Once this is 0, this limit exists and the function is going to be differentiable. So, x power n minus 1 should not tend to 0 as x tends to 0. So, n minus 1 should be less than or equal to 0. N minus 1 should be less than or equal to 0. So, for the given question, the function is continuous but not differentiable only when n is greater than 0 and also when n is less than or equal to 1. Both of them should be true. So, n has to be between, both of them put together, n has to be between open 0 to closed 1. N is less than or equal to 1, n is greater than 0, put together n belongs to open interval 0 to 1. That is answer A. Next question, if f of x is equal to mod x minus mod x minus 1 whole square, then find f dash of x. If f of x is equal to mod x minus mod x minus 1 whole square, find f dash of x. To evaluate this question, we can do it with modulus present directly, or we can also remove the modulus and do the question. So, let us do it by the second method, where we remove all the modulus symbols and then start differentiating the function. So, in the question, f of x is given mod x minus 1 whole square, and we are asked to find f dash of x. We have to differentiate this function. For that, first let us remove all the modulus signs. So, mod x can be properly defined when we know whether x is greater than 0 or less than 0, and mod x minus 1 can be defined when we know x is greater than 1 or less than 1. So, let us cut the number line into 3 cases: x less than 0, x lying between 0 and 1, and x greater than 1. First case, when x is less than 0, mod x will be minus x, because x is negative, mod x will be minus x. X is negative, so x minus 1 is also negative. So, mod x minus 1 is 1 minus x. Whole square. Minus x, minus of minus plus x, x and x gets cancelled. We are left with minus 1 whole square, which is 1. So, f of x is a constant function whenever x is less than 0, and derivative of f dash x will be 0. So, whenever x is less than 0, f dash x is equal to 0. Let us look at case 2. Let us look at case 2, that is when x lies between 0 and 1. X lies between 0 and 1. Whenever x is greater than or equal to 0, mod x is x. X is less than 1, so x minus 1 is negative. Mod x minus 1 will be 1 minus x. With minus sign, it is x minus 1. So, we have 2x minus 1 whole square. F of x is 2x minus 1 whole square, and differentiating this, f dash x will be 2 into 2x minus 1 into derivative of 2x, which is 2, so it is 4 into 2x minus 1, 4 into 2x minus 1. So in case 2, when x is between 0 and 1, f dash of x will be 4 into 2x minus 1. Let us look at the last case, case 3, that is when x is greater than 1. When x is greater than 1, x is obviously positive, so mod x is x. X is greater than 1, so x minus 1 is also positive. So mod x minus 1 is x minus 1. X and x gets cancelled. We have 1 square, f of x is 1, f of x is a constant function, so f dash x is 0. So whenever x is greater than 1, f dash x is again 0. So f dash x is 0 when x is less than 0 and also for x greater than 1, and whenever x lies between 0 and 1, f dash of x is 4 into 2x minus 1. So our answer is f dash x is 0 for x less than 0 and for x greater than 1, and f dash of x is 4 into 2x minus 1 for x lying between 0 and 1. So answer is C. Next question, if integral pi by 2 to x root over 2 minus 2 sin square t plus integral 0 to y cos t dt is equal to 0, then find dy by dx at pi comma pi. Question reads, integral pi by 2 to x root over 2 minus 2 sin square t dt plus integral 0 to y cos t dt is equal to 0. This is an implicit relation in terms of x and y. Integral pi by 2 to x root over 2 minus 2 sin square t dt plus integral 0 to y cos t dt is equal to 0. Then we need to find dy by dx when x is pi and y is pi at pi comma pi. So let us do this differentiation. Let us understand this function properly. Root over 2 minus 2 sin square t. Root 2 can be taken common. Integral pi by 2 to x root over 1 minus sin square t is root over cos square t, and root over cos square t is not cos t, it is mod cos t. So we should not forget modulus here. Root over cos square t is mod cos t, not simply cos t, plus integral 0 to y cos t dt. This is given to be 0. Now let us understand the question. We are finding derivative at x is equal to pi. So we are investigating this function in the neighborhood of pi, and the neighborhood of pi is either second quadrant or third quadrant. Values of t which are greater than pi will fall in third quadrant, and values of t which are less than pi fall in second quadrant. In either of the quadrants, cos t is negative. So mod cos t is minus cos t. Mod cos t is minus cos t. Now modulus is removed. Let us differentiate this equation throughout, and for this, because we have to differentiate a definite integral, we have to use Newton-Leibniz rule, which says minus root 2 as it is into derivative of this function with respect to x is derivative of numerator upper limit 1 into substitute upper limit in place of t cos x minus derivative of lower limit is 0, substitute lower limit 0 into whatever is 0. So minus root 2 cos x plus differentiate integral 0 to y cos t dt with respect to x. Derivative of upper limit dy by dx into substitute upper limit cos y, derivative of lower limit 0 into whatever is 0. So this equation minus root 2 cos x plus dy by dx into cos y is equal to 0. We want dy by dx when x is pi and y is pi. So let me substitute x equal to pi. What I get is minus 1 root 2 plus cos of pi is minus 1 minus dy by dx is 0, or dy by dx is equal to root 2. Dy by dx is root 2. So answer is B. Next question. If alpha and beta be the roots of equation ax square plus bx plus c equal to 0, then find limit extending to alpha 1 plus ax square plus bx plus c whole to the power 1 by x minus alpha. Alpha and beta are given to be roots of ax square plus bx plus c equal to 0, and we are asked to evaluate limit extending to alpha, limit extending to alpha 1 plus ax square plus bx plus c whole to the power 1 by x minus alpha. There is a question on one factor theorem. Alpha and beta are roots of ax square plus bx plus c. Then x minus alpha is a factor of ax square plus bx plus c, and x minus beta is also a factor of ax square plus bx plus c. So alpha and beta, because they are factors of ax square plus bx plus c, we can write ax square plus bx plus c as a into x minus alpha into x minus beta. From factor theorem, because alpha and beta are roots of ax square plus bx plus c equal to 0, ax square plus bx plus c can be written as a into x minus alpha into x minus beta. Now, as x tends to alpha, ax square plus bx plus c tends to 0. So 1 plus ax square plus bx plus c tends to 1, and power tends to infinity. So this is 1 power infinity form. This is 1 power infinity form. And in every 1 power infinity form, limit extending to a, f of x power g of x, limit extending to a, f of x power g of x, in 1 power infinity form, we write it as limit extending to a, f of x minus 1 into g of x e to the power of. Whenever we have 1 power infinity form, limit extending to a, f of x power g of x will be written as e power limit extending to a, f of x minus 1 into g of x. Let us use that here. So our limit will be e power limit extending to alpha, f of x minus 1. So from this, if I subtract 1, I will be left with ax square plus bx plus c into g of x is 1 by x minus alpha. And from the result of factor theorem, we know we can replace ax square plus bx plus c by a into x minus alpha into x minus beta. Now we can see x minus alpha and x minus alpha are getting cancelled, and as x tends to alpha, this is a into alpha minus beta. So our answer is e power a into alpha minus beta. Answer is e power a into alpha minus beta, which is option C. Next question. If f of x is differentiable and strictly increasing function and f dash 0 is not equal to 0, then find the value of limit extending to 0, f of x square minus f of x divided by f of x minus 0. It is given that f of x is differentiable, f dash 0 is not equal to 0, f of x is strictly increasing function, and we are asked to find the value of limit extending to 0 f of x square minus f of x divided by f of x minus f of 0. Now let us see, as x tends to 0, f of x square is f of 0, f of 0, f of 0, f of 0. This is 0 by 0 form. So in this, we can apply L'Hospital rule. F of x is given to be differentiable and numerator is tending to 0, denominator is tending to 0. So this is a direct question on L'Hospital rule. Limit x tending to 0, f of x square minus f of x divided by f of x minus f of 0. We can differentiate the numerator. Derivative of f of x square is f dash of x square into derivative of x square 2x minus derivative of f of x is f dash of x divided by derivative of denominator f dash of x minus derivative of a constant is 0. So we have limit extending to 0 2x f dash of x square minus f dash of x divided by f dash of x. Now f dash of x is non-zero number. F dash of x is non-zero number. Let us say a. As x tends to 0, f dash x is a. X square is also 0. So this is also a. This is also a. And because a is non-zero, we can cancel that a throughout and we will be left with a small limit extending to 0 2x minus 1, and limit extending to 0 2x minus 1 is minus 1. So as x tends to 0, because f dash x is non-zero, f dash x square, f dash x and f dash x can be cancelled throughout, and this limit it will be minus 1. So it's option C. Next question, if f of x is equal to x square plus 5x plus 3 divided by x square plus 2x plus 2 whole power x, then find limit extending to infinity f of x. F of x is given to be x square plus 5x plus 3 divided by x square plus x plus 2 whole power x. We need to find limit extending to infinity f of x. F of x is given to be x square plus 5x plus 3 divided by x square plus x plus 2 whole power x. We need to find limit extending to infinity f of x. Now, as x tends to infinity, we can see x square plus 5x plus 3 divided by x square plus x plus 2 tends to 1. As x tends to infinity, numerator and denominator are both polynomials of same degree. So this answer will be coefficient of x square in numerator divided by coefficient of x square in denominator, which is 1, and power is x, which is tending to infinity. So it is 1 power infinity form. And whenever we get a 1 power infinity form, limit extending to a f of x power g of x, we can write it as e power limit extending to a f of x minus 1 x square plus 5x plus 3 divided by x square plus x plus 2 minus 1 into g of x, which is x. So this limit will be e power limit extending to infinity, take LCM, x square gets cancelled, 5x minus x is 4x, 3 minus 2 is 1 into x, 4x square plus x divided by x square plus x plus 2. As x tends to infinity, numerator is a quadratic, denominator is a quadratic, x square coefficient is 1 here, x square coefficient is 4 here. So this will be e power 4. Our answer is e power 4. So Answer is option D. If f of x is equal to minus 1 if x is less than 0, 0 if x is equal to 0, and 1 if x is greater than 0, and g of x is equal to sin x plus cos x, then we need to find the points of discontinuities of f of g of x in 0 to 2 pi. F of x is given to be minus 1 if x is less than 0, 0 if x is equal to 0, and 1 if x is greater than 0, and g of x is given to be sin x plus cos x. We need to discuss continuity of f of g of x in 0 to 2 pi, and both the numbers are excluded, 0 to 2 pi. Now, to talk about f of any number, we need to know whether that number is less than 0 or equal to 0 or greater than 0. That is, we need to know whether the number, when it is positive, when it is negative, and when it is 0. So, in order to talk of f of g of x, I need to know when sin x plus cos x will be positive, when sin x plus cos x will be negative, and when sin x plus cos x will be 0. So, let us cut the quadrants into two parts each. Let us get all octants. 0 to 2 pi, all the numbers from 0 to 2 pi. Let me cut the quadrants into further two parts each, and let me split them into 8 octants. In first octant, that is when x lies between 0 to pi by 4, sin x is positive, cos x is positive, sin x plus cos x will be positive. And also in the second octant, sin x is positive, cos x is positive, sin x plus cos x will be positive. In third octant, sin x is positive, cos x is negative. This is second quadrant. Sin x is positive and cos x is negative. So, the sum in second quadrant could be positive or negative depending on whether magnitude of sin x is more or magnitude of cos x is more. As the angles are closer to pi by 2, closer to y axis, magnitude of sin x will be more than magnitude of cos x. So, here the positive number is more in magnitude, sin x is more in magnitude than the negative number cos x, so sum will be positive. And in this octant, cos x will be more in magnitude compared to sin x, so sin x plus cos x will be negative. In third quadrant, sin x is negative, cos x is negative, so sin x plus cos x will be negative. In fourth quadrant, cos x is positive, sin x is negative. Magnitude of cos x is more when it is closer to a multiple of pi. So, in this octant, cos x is more in magnitude and cos x is positive. So, sum of sin x plus cos x is positive, and here it is negative. So, whenever x varies from 0 to 3 pi by 4, in the region when x is between 0 and 3 pi by 4, sin x plus cos x is positive. So, f of g of x, we can say whenever x is between 0 and 3 pi by 4, 3 pi by 4 not included, g of x is positive. So, f of g of x will be 1. And when x is 3 pi by 4, sin x plus cos x is 0, and because sin x plus cos x is 0, f of 0 it will be 0. Now, from 3 pi by 4 to 5 pi by 4, from 3 pi by 4 to 5 pi by 4 to 7 pi by 4, from x equal to 3 pi by 4 to 7 pi by 4, sin x plus cos x, it is negative. Sin x plus cos x is negative. So, g of x is less than 0 or f of g of x is minus 1. f of g of x is minus 1. Again, from 7 pi by 4 to 2 pi, 7 pi by 4 to 2 pi, sin x plus cos x is positive. So, f of g of x will be 1. So, now we have the definition of f of g of x. F of g of x is 1 if x belongs to 0 to 3 pi by 4 or when x belongs to 7 pi by 4 to 2 pi. F of g of x is 0 when x is 3 pi by 4 or even when x is 7 pi by 4. F of g of x is minus 1 from x 3 pi by 4 to 7 pi by 4. So, we have 2 points of discontinuity, 3 pi by 4 and 7 pi by 4. At 3 pi by 4, functional value is different from left hand limit to right hand limit. At 7 pi by 4, functional value is different from left hand limit to right hand limit. So, the function is discontinuous at 2 points, and that is 3 pi by 4 and 7 pi by 4, which is answer C. Next question, the value of the derivative of mod x minus 1 plus mod x minus 3 at x equal to 2. We want derivative of mod x minus 1 plus mod x minus 3 at x equal to 2. Let us call this function f of x. Let f of x be mod x minus 1 plus mod x minus 3, and what we need is f dash of 2. Now, in the neighborhood of 2, let us define the function f of x in neighborhood of 2. In neighborhood of 2, x minus 1 is positive, x is close to 2, so x minus 1 is positive, x minus 3 is negative. Mod of x minus 1 will be x minus 1, and mod of 3 minus x minus 3 is 3 minus x. As x minus 1 is positive in the neighborhood of 2, mod x minus 1 is x minus 1 itself, and as x minus 3 is negative, mod of x minus 3 is 3 minus x. X and x gets cancelled. So, f of x is a constant function 2 in the neighborhood of 2. F of x is a constant function 2 in the neighborhood of 2. So, f dash of 2, we can say it is 0. So, f dash of 2 is 0, answer is B. Next question, G maps R to R, G of x is equal to cos inverse of sine of f of x. G of x is equal to cos inverse of sine of f of x has exactly 2 elements in range set. Then option A, f of x must be discontinuous function. Option B, f of x may be continuous function. Option C, it's not possible to have such a function. Option D, f of x is discontinuous at finite points only. G maps R to R, G of x is equal to cos inverse of sine of f of x. G of x is equal to cos inverse of sine of f of x has exactly 2 points in range set. Exactly 2 points in range set. So, cardinality of range of G is 2. Then we have to look at the options. Option A, f of x must be discontinuous function. Option B, f of x may be continuous function. So, we have to discuss on continuity of f. It is not possible to have such a function. And option D, f of x is discontinuous at finite points only. Now, let us see, g of x is cos inverse of sine of f of x, and in the range set we have only 2 points. We have only 2 points. So, let us assume f of x to be a continuous function, and also it is given that G maps R to R. G maps R to R. Range of this domain of this function is R. Domain of this function is R. So, f of x should be meaningful for all values of R. f of x should be defined on R. And moreover, cos inverse of sine of f of x should have only two elements in the range set. It should have only two elements in the range set. Let us for a while assume that f of x is a continuous function. Let us assume f to be a continuous function. Now, if you see a continuous function, its range will either be a single point set, it will be a singleton set, it will have only one element in it, or it will be an interval. If it is a constant function, a continuous constant function will have only one element in its range, it will be a singleton set, or if it is not a constant function, then it will contain an interval. Now, cos inverse of sine of f of x, let us say f of x contains only one element, then g of x will also have a single element in its range, whereas cardinality of g is given to be 2. So, it is not possible for f to be a constant function. Let us assume that range of f is an interval. When range of f is an interval, then cos inverse of sine of f of x will also give you a range which is an interval. I am substituting an interval in sin x. My output will be an interval, and this inside cos inverse will also give me an interval. So, it cannot give me cardinality of range to be 2. So, f of x cannot be a continuous function. Our assumption that f of x is a continuous function is wrong. So, by contradiction, we can say f of x has to be a discontinuous function, and discontinuous not just at finite points, but at infinitely many points. So, it's answer A. Next question, limit n tending to infinity n into cos of pi by 4n into sin of pi by 4n is equal to k. Limit n tending to infinity n into cos of pi by 4n into sin of pi by 4n is equal to k. We need to find the value of k. Limit n tending to infinity, as n tends to infinity, we all know 1 by n tends to 0. So, let us look at the question, n into cos of pi by 4n into sin of pi by 4n is given to be k, and we know that as n tends to infinity, 1 by n tends to 0. So, pi by 4n as n tends to infinity tends to 0. Cos of any number tending to 0 is 1. So, cos of pi by 4n we can replace it with 1. Cos of pi by 4n we can replace it with 1. As n tends to infinity, this 1 I can write it as 1 by n. 1 by n tends to 0. As n tends to infinity, 1 by n tends to 0. Now, 1 by n I can see it as some x, and as n tends to infinity, x tends to 0, x. Now, you can see simple limit extending to 0 sin ax by x, which is a, or k has to be pi by 4. So, answer is pi by 4, which is our option B. Next question, the function f of x is equal to 1 if mod x is greater than or equal to 1, 1 by n square when mod x lies between 1 by n and 1 by n minus 1, and 0 when x is equal to 0. Function f of x is defined as 1 if mod x is greater than or equal to 1, 0 if x is 0, and 1 by n square whenever mod x lies between 1 by n and 1 by n minus 1, where n can be any number of the form 2, 3, so on. Now, we need to talk about continuity of this function. So, for that, let us understand this function on a graph. Let us plot graph of this function. Now, entire discussion is in terms of mod x. So, this function is an even function. F of x definition, when mod x is greater than or equal to 1, it is 1, and whenever mod x lies between two numbers, it is 1 by n square. So, it is an even function. F of 0 is given to be 0. F of 0 is given to be 0. Whenever mod x is greater than or equal to 1, that is when x is greater than or equal to 1 or x is less than or equal to minus 1, mod x is defined as 1. So, it is a constant function in the interval minus infinity to minus 1 and from 1 to infinity. Now, let us focus on the interval when mod x lies between 1 by n to n minus 1. Let us start our discussion with n equal to 2. When mod x lies between half and 1, f of x is given to be 1 by 2 square 1 by 4. So, in this interval again it is a constant function 1 by 4, and equality here is given with 1. Now, let us see what is f of x when n is 3. If mod x lies between 1 by 3 and 1 by 2, that is from 1 by 3 to 1 by 2, f of x is given by 1 by 9. 1 by 9 is a much smaller number. So, we can see from 1 by 3 to 1 by 4, it will be 1 by 16. And we will have some diminishing line segments, diminishing in size. So, it is difficult to plot the graph in the neighborhood of 0. Now, we can talk about continuity of this function. This is obviously not continuous everywhere. We can see at many points the function is breaking. We cannot draw the graph without lifting the pen. And also, it is discontinuous at infinitely many points, at every number of the form 1 by 3, 1 by 4, 1 by 5, 1 by 6, 1 by 7, so on. It is discontinuous. So, the function is discontinuous at infinitely many points, or the answer is option A. If f of x is equal to 1 plus x minus integral part of x and g of x is equal to mod x by x if x is not equal to 0 and 0 if x is equal to 0, h of x is equal to g of f of x, then we need to find h dash of 1 and h dash of minus 1. F of x is given to be 1 plus x minus integral part of x, which is 1 plus fractional part of x. G of x is given to be mod x by x if x is not equal to 0 and 0 if x is equal to 0, and h of x is defined as g of f of x. H of x is defined as g of f of x. We are asked the values of h dash of 1 and h dash of minus 1. We are asked the values of h dash of 1 and h dash of minus 1. F of x is 1 plus fractional part of x. We know fractional part of x is a number between 0 and 1. Fractional part of x will always lie between 0 and 1. So, f of x is a number which will always lie between 1 and 2. F of x will always lie between 1 and 2. Our range of f of x is closed interval 1 to open interval 2. Let us understand g of x. G of x is 0 whenever x is 0 and g of x is mod x by x whenever x is not 0. That is, if x is positive, g of x is mod x by x, which is 1. Whenever x is positive, g of x is 1. and whenever x is negative, g of x is minus 1. Whenever x is negative, mod x is minus x and g of x is minus 1. Now, h of x is g of f of x. To understand g of f of x, we need to know whether f of x is 0 or non-zero. If it is non-zero, whether it is positive or negative. But f of x we have seen 1 plus fractional part of x, range of f is 1 to 2, which is always positive. So, we can say g of f of x is always 1. G of f of x is always 1. F of x is always positive, and whenever x is positive, g of x is 1. So, g of f of x is 1. H of x is a constant function 1, and derivative of h dash x, h of x is always 0. So, h dash 1 is 0 and h dash minus 1 is also 0. So, our answer is both of them equal to 0, option A. Let f of x be differentiable function with f dash 1 equal to 4 and f dash 2 is equal to 6. We have to evaluate limit f of 2 plus 2h plus h square minus f of 2 divided by f of 1 plus h minus h square minus f of 1 as h tends to 0. We are given f dash 2 is equal to 6, f dash 1 is equal to 4, and we are supposed to evaluate limit h tending to 0 f of 2 plus 2h plus h square minus f of 2 divided by f of 1 plus h plus h square minus f of 1. See, as h tends to 0, f of 1 plus h plus h square, 1 plus h plus h square tends to 1, f of 1 minus f of 1 is 0, and numerator 2 plus 2h plus h square tends to 2. So, f of 2 minus f of 2 is 0. It is a 0 by 0 form, and also it is given that f of x is differentiable. So, we can apply L'Hospital rule. Limit h tending to 0 f of x by g of x is same as limit h tending to 0 f dash x by g dash x. So, let us differentiate numerator. Derivative of f of 2 plus 2h plus h square is f dash of 2 plus 2h plus h square into derivative of 2 plus 2h plus h square is 2h plus 2 divided by derivative of the denominator f dash of 1 plus h square into derivative of 1 plus h square is 2h plus 1. So, as h tends to 0, we have 2 plus 2h plus h square tending to 2, and f dash of 2 is 6. So, our answer would be 6 into, as h tends to 0, 2h plus 2 tends to 2 divided by 1 plus h square as h tends to 0 is 1, and f dash of 1 is given to be 4 into 2h plus 1 is 1 as h tends to 0. So, our answer is 3, and it is option B.